Yes, welcome everyone. I'm very happy to introduce Bo Zeng today. He's our speaker for this week. He's associate professor at the University of Pittsburgh. His research is focused mostly on discrete and robust optimization, especially also distributional robust optimization, often with applications in logistics, energy, and healthcare. And he's very famous for his work on the famous column and constraint generation algorithm, which I use a lot already in my career. So very honored to have you here. And besides all the research, he's also a professional member of the IISE, the Informs, and the IEEE. And please, Bo.
Thank you, Yanis. Really appreciate you folks' invitation, and it's a great honor to be able to present in this robust optimization webinar. Also, thank you for the audience from around the world, regardless the time zone. I know some of them, the time zone may not be friendly. So the topic today I'm going to present is a study on the distribution robust optimization from a primal perspective, and which lead to an intuitive, complete, and extendable solution framework. This is a joint work, mainly a joint work with my former student, Zhongzong Lu. And this agenda of today's presentation, I'm going to have six sections to cover different perspectives. And after this presentation, I can address the question from you folks. Okay. So let's have a quick intro for the distribution in robust optimization. I believe our audience, many of you already have some access or some basic background on DRO, but here, in case some of you folks don't have much background yet, I just quickly go through, which also provide a basis for me to describe our solution framework. Here I give you the standard simple structure of the DRO. So in object function, we try to min max. Min is the one we can control. Max is the something controlled by the God or by the nature. They try to identify a distribution that is maximize our. We want to minimize, but God is trying to select some distribution that is maximize our loss function. Let's say here the random parameter is represented by the Kasi. We know Kasi is random, but we don't know the exact distribution behind the Kasi. Rather, knowing the exact distribution, we know the distribution follows, the distribution belongs to a family of the distributions, which is represented by the calligraphy P. So you folks can see, let me, let me start the annotation part. So I can be with you. I'll give you some additional support. Okay. So this let me test. This is the family of the distribution. This as right now, since it's a family of distributions, it contains not only a single distribution, actually it contains maybe infinite number of distributions. To support our duration, we make one assumption. We say the capital C, which is a sample space, which is compact in our study. But here I want to highlight we are not talking about the support. We are talking about we are using capital C to represent sample space. As you folks probably know, there's a difference. Support is subset of sample space. A sample space in the sample space we may have some scenarios or atoms that does not that do not have any probability on it, but support is defined by the subset such that unimportant in the support may receive some non-zero probability. So that's difference. The reason we introduce this difference is we may in the future we may see the scenarios it happen to with no distribution on it. It happens to have no mass on it. So this is going the standard DRO in the literature currently. Uh, Based on literature, we have seen people, uh, we have seen a lot of work on DRO. They have um, generated a lot of insights regarding the effectiveness or usefulness of a DRO. Basically, we can treat DRO as a bridge between stochastic optimization and the robust optimization. So from the robustness point of view, it is stronger. DRO gonna generate solution which is more robust than the solution produced by the SO. But compared with RO, it is less conservative because RO actually is notorious for being too conservative. But compared with RO, DRO produce solution which is less conservative. So this is compared with these two classical methodology. DRO it can be see a bridge and can be can produce a nice trade-off between them. Another part I want to highlight is people talk about using data-driven concept to uh, as a motivation to build DRO. So that means DRO can not only leverage the existing data, but it can also beyond the current data available. The reason is it can hedge against the unforeseen randomness beyond the current data. So overall, it provides a better generalization. So that's reason DRO as a concept, as a mathematical tool, it is highly treated in our literature, in our optimization society. And today we're going to talk about the main focus of our presentation is about two-stage DRO. So instead of have a like a min-max structure in the object function, right now we have a more sophisticated one, turns out to be a tree level. We still have a min-max, but after the min-max, we're going to have a recourse problem. So here I'm using X to represent the first stage decision, which is also called here the null decision. And Y variable uh, is introduced to denote the recourse decision, which is also called wait and see decision. Between them, we have a randomness. So that means after randomness is observed, we can have a recourse, we can have a mitigation. So the whole framework make it more flexible and applicable in real life, especially for the sequential decision making. Okay. So the solution will be more cost effective and less conservative. It's a nice framework. However, the structure is non-trivial because it contains a nested structure. So it's way much harder to solve. And in the literature, we also see a lot of progress on this regard. Many substantial, wonderful papers have been appeared in the literature. They are theoretically deep and technically very solid. And indeed, I had to admit that some papers are very solid, very deep, and I have a hard time to fully understand them. I really appreciate those sophisticated, solid math development. And another part is we have seen uh, a few, several well-designed algorithms to address this complex tree-level model. And however, they are, I have to admit, they are mathematically heavy and they are not so intuitive yet. So we generalize a few barriers with a few issues behind those current literature. One is, as I mentioned, mathematics very heavy, and so it's not friendly to practitioners. They may have a hard time to understand a lot of deep duality-based operations. And another part is that our computation capacity may not so strong yet. In the literature, I have seen very often the number of observations we can handle, it's just like 10 samples. So may not be able to convince the practitioner to adopt this powerful methodology. And up to now, the popular assumption in the literature is recourse is always feasible. So for any given process state decision, we just assume regardless the realization of the scenario, the recourse is feasible. But that may not address the real life concern. Sometimes the recourse could be infeasible. So given that, we have to restrict our choice on the first state decision. The last one is so far all the ambiguous set are assumed to convex regardless the sample space is discrete or continuous, but they are convex. So we are thinking maybe this is another restriction. We probably sometimes we have to deal with non-convex ambiguous set. But so far in the literature, this part has not been discussed yet. So with those issues in the literature, at this moment, DRO, regardless the fact it is so powerful, so great, but it's conceptually and computationally wise, it's not widely adopted yet. So we are thinking we probably need to come up some algorithms to address this current situation. So our goal is to develop some simple, intuitive, and stable algorithm that can be applied in real life. To support, excuse me, let me drink a little bit of water. To support our development, maybe it's good time to review quickly, spend a couple minutes, review some ideas we have done before to address the two-stage robust rotation. As you folks can see, it's also a tree level model. It's a min-max mean structure, but we don't have a expected value anymore, so it's simpler. So the difference between DRO and RO is here, instead of consider expected value or distributions, we consider the worst case scenario inside an uncertain set. But still, it's a difficult tree level structure, hard to compute. So recall, I mean, to address this simpler but still challenging formulation, what we did is we try to build deep insight how to analyze the structure. The first step we did is try to be silly. Okay. The reason we say try to be silly is just enumerate. Let's assume right now the uncertainty set actually is a collection of finite scenarios. So let's use U1 up to UN to represent this set of finite scenarios. Given this is a finite set of scenarios, so we can do enumeration. Okay, let's be silly and do enumeration. So we can reduce this tree level model into a single level model. Actually, this part. And but we lose we can get rid of the complexity implied by the min-max mean structure, but as a result, we have to deal with a very large scale mixed integer program. So although it's large scale, but we can gain a deep insights. So that's the idea behind the development of the solution algorithm for two-stage robust rotation. Okay. As we just mentioned, it's a large scale mixed integer program. We don't like to handle it because the capital U, the set of the scenarios could be large. So we don't want to directly compute this large scale one. So let's be a little bit smarter. Just consider a subset. So instead of doing the full enumeration, let's consider partial enumeration. And the size of the partial enumeration actually is controllable by us. But the good part is this partial enumeration help us to build a deeper insight, because this sub enumeration provide a relaxation, and it's controllable relaxation. So with this controllable relaxation, actually we can have a lower bound compared to the original two-stage RO. Okay, and this low bound, yes. But you may wonder the low bound, is it good enough? So to check the strength of the low bound, we have to solve a subproblem. Here, this one is we define the mass problem. Okay, we have to solve the subproblem. Okay, actually the subproblem provides two functions, as we can see next page. One is to evaluate provide evaluation. I'm sorry. Another one is to provide a new scenario, because if the low bound is probably too weak, we can generate a new scenario to strengthen our low bound. So this is a whole framework. We call it a Coulomb constraint generation. the idea behind is the main idea behind is every time we generate a new scenario to expand our partial enumeration, so we can increase the lower bound. And same time, by solving the subproblem, we can, as I mentioned, provide a better, likely to provide a better upper bound. So, and we can do this iteratively until the difference between lower and upper bound is very small. Yeah. When we generate sub scenario, we keep in mind we do not fix y, we do not fix the variable. Actually, we let y still being a variable. So it's matched with our initial reformulation by enumerating all the scenarios. Given the last 12 years, 13 years, we have seen CCG has become very useful in practice. We have heard a lot of comments from practitioners and researchers. One great advantage is it starts from a Primal perspective. So before CCG, Benders actually used as a popular methodology to deal with excuse me, to deal with robust rotation. But with CCG, people realize it is more intuitive to understand because every time we generate a scenario in the answering set, so it's kind of intuitive to appreciate the idea behind. And the second one is the logic is simple and the structure is simple. So it's kind of easy to implement. As we show in our previous work, it's guaranteed, convergence guaranteed. And also it's much faster than bend-still type of cutting plans. So far we have seen it's being applied in thousands of the different applications. So it's practically verified, and people believe it's a strong methodology to handle the complex two-stage RO. And actually, I have seen several papers using CCG directly to solve the two-stage DRO. But after we start working on DRO, we are thinking just the CCG enough to deal with two-stage DRO, or we have to do some additional customization. Can we make a further improvement? So that's the motivation inspire us to think about can we speed up the computation by leveraging the structure of CCG. Okay. Indeed, we found probably can leverage a deeper structure behind the two-stage DRO to speed up the computation of the CCG. The key part behind this customization is how to solve the worst case distribution from the Primal perspective. So let's single out the worst case expected value problem, which is a subproblem inside our whole framework. The idea is for given x, how to identify the worst case distribution rather than identify the worst case scenario. In the previous RO, we were talking about identify the worst case scenario, but here we're talking about how to identify the worst case distribution. So we define this problem, a worst case expected value problem. Here we do not consider x. Let's just focus on this problem, how to identify the worst case expected value. And as you folks can see, it involves a complex integration operation over over the capital C. And so the problem is hard to compute, but we are not so smart. So we're thinking, so instead of computing the integration, which is complex, what about we go back to our fresh year calculus concept? Instead of doing the integration, let's consider integration as a sum. So this is a basic concept we adopted in our derivation. We noticed for any distribution, we can approximate or we can approaching with by limiting regarding a summation of over a set of discrete scenarios. So as you can see, this we're talking about a summation or a summation of a set of finite scenarios, and but when the number of scenarios goes to infinite, these two parts were equal. So the integration can be replaced by consider a summation or a finite set of scenarios. But the question is how to identify those scenarios. Okay. And actually we can prove for any epsilon, there exists such a discrete distribution. So that make the whole things computationally viable. Okay. So this is the idea behind. So we don't deal with integration. We simply try to identify the scenarios behind. Try to identify a set of finite scenarios behind. Okay. Let me move to next page.
One question, Bo.
Yes.
This uncertainty set psi, so it's the support now. Is it a convex set or a discrete set? So you're choosing the
It's continuous. It's convex.
okay, so
So
you
it's yeah.
choose the
It's
maximum is choosing the scenarios from a convex set, which are maximizing the.
yeah.
Okay,
Yeah.
great, thanks.
Yeah, if it's discrete in real life, as we mentioned, it's a compact, so we don't need to do the limit. It's just like a we can remove limit,
Yeah,
right? Right. But here we talk about actually we don't have any restrict assumption unless just assume cosine is a capital cosine is a compact set. So we can deal with both the discrete sample space as well as the continuous sample space.
yep, thanks.
Okay, thank you. So we would let's pick up a representation of our ambiguous set. If you folks recall, we have this at the beginning. This is our ambiguous set. So we want to consider the general case. So we have a we have a M, no not more than one. We have M type of such constraints uh, to help us to characterize the family of the distributions. This psi actually is a psi is a uh, value and bounded function, so it's a kind of general. Here the calligraph M is the measure O is the collection of the O measures over a cosine. So we feel like this one is general, so it can represent the popular moment and the Watson distance inequalities. Uh, and for this one, actually, there's a classical result proposed by Alexandra Shapiro in 2001. In this paper, they mentioned they show that under mild condition, the worst case distribution, the worst case expected value has an optimal solution with at most m plus one scenarios. So here we have m constraints plus this integration equal to one constraint. Together we have a m plus one constraint. So this paper shows that we in the worst case distribution, at most m plus one scenarios will receive non-zero probability. So that's provided like a theoretical support to guarantee the worst case distribution actually can be replaced by m plus one, can be replaced by a finite number of scenarios. So by leveraging this result, actually this result has been there for this year is 2026. So this result has been there for 25 years, but this result has not been heavily used. So instead of treating this result as a theoretical result, we're thinking, let's be a little bit silly, just try to use it. So what we did is, oh, I'm sorry. By giving this observation, given this theoretical insight, let's introduce m plus one variables. Actually, m plus one pair of variables. We treat scenarios and the variables. I'm sorry, we treat scenarios and its probability, both of them as variables. So by doing this, we can convert the worst case value into a finite mathematical program. So instead of have a integration, everything can be reduced to a finite mathematical program. And it's friendly for us to compute because as optimization, we don't want to deal with infinite things. We want to deal with finite type of stuff. And this structure is simple. And sometimes it can be solved by solver. So we call this idea as Oracle 1. But this one is the formulation is challenging, and it naturally involves a bilinear structure because, as I mentioned, both of them are variables. So we can see the product between them. So it's a bilinear structure. Sometimes could be higher order polynomial. So computation-wise, it's not friendly for us, even for the state-of-art solver. I have some numerical results for you for us to appreciate the computation challenge. So instead of using Oracle 1, uh, we're thinking another one, which is a column generation. Because as you folks recall, I mentioned it's we can treat it as this one as a summation or many scenarios. Since we have many scenarios, so the then we are thinking to deal with the many scenarios, we can use column generation. And indeed, once the scenarios are fixed, it's LP. So column generation actually is the ideal methodology to deal with this huge linear program. As a column generation is a very classical methodology in the literature, I guess I can quickly, I don't need to go to the details. I just provided the main idea. Uh, in order to customize column generation for our worst case expected value problem, we introduce two problems. One is a pricing mass problem. If you know a little bit about column generation, probably you will understand what is pricing. So pricing mass problem is the try to identify for a given set of scenarios, try to identify the largest value. Okay, and keep in mind is for a given set of scenarios, but the scenario may not be sufficient. So we're gonna use pricing subproblem to identify the new scenarios. So we do it until the reduced cost is less or equal to 0. So this is the basic idea behind. Uh, Between these two, we call this one Oracle 2. So between these two oracles, we have a few comments. So we note Oracle 1 is theoretically clear. It's suitable for ending follow-up proofs. And also for Oracle 2 under some mild conditions, we can prove Oracle 2 terminate in finite number iterations. And indeed, the pricing subproblem of Oracle 2 resembles the subproblem of a CCG because it generates extreme point of Cassini if all the psi functions are linear and the sample space is a polyhedral. One more important part is we notice both of them can handle the non-convex ambiguous set. If the ambiguous set is non-convex, probably we have to use the mixed integer set to represent this non-convex ambiguous set. But for Oracle 1, we can easily extend easily extend the Oracle 1 to make it as a mixed integer nonlinear finite mathematical program. But indeed, its computation is very challenging. But for Oracle 2, we note it can be we can extend it to the conversion to branch and price, which is another classical OR technology. So these two oracles can be used together to address the non-convex mixed set. Right? And as I mentioned, this non-convex mixed set has not been studied in the literature yet. So right now, once we address the how to identify the scenario and the probability behind the worst case value, right now we can integrate this part with the CCG. Again, we have a mass problem, but right now we call it the main mass problem, and also we have two subproblems. One is for optimality, one is for feasibility. This whole framework has a couple of features we want to mention. One is we can deal with a feasibility issue right now, and the scenario generation will be done by using the two oracles, each one of them we just mentioned, and we can prove the finite convergence. So let's talk about the specific part of our framework. So in the mass problem, in the main mass problem, we are given a set of a finite set of scenarios. So for the given finite set of scenarios, we can build this bilevel model. The low level model is how to, given the current scenarios, how to identify the probability for those scenarios, such that we can maximize the expected cost in the second stage. But this bilevel model actually is very simple. So this this main mass problem provides a low bound, but it can be easily addressed by applying some duality or KKT condition type of reformulation to convert this whole thing into a mixed integer program. So next page, I'm gonna show you the structure of the after the KT condition or strong duality. Here we are using strong duality. Actually, here we notice that by using strong duality, there's no big M. We don't need to worry too much. Okay. We still have eta, and here we have alpha and beta. Those are dual variables associated with the constraints in the low-level problem. And this one actually resemble the duality-based reformulation literature, but the good part is it's based on the finite scenarios, and as we just mentioned, eta capture the largest expected value achievable over those finite scenarios. Okay. It's a lower bound, but again, we may not be able to happy with the lower bound, so we want to generate more scenarios. But first question we need to answer is the solution from the mass problem, is it feasible? As we mentioned, the feasibility has not been addressed in the literature yet. Excuse me. To support our understanding of the feasibility issue, we introduced the feasibility certificate, which can be done by introducing artificial variable y tilde. Y tilde is here, which is used to guarantee feasibility of the recourse problem. So the new recourse problem is we define new recourse problem is to minimize the L1 norm of y tilde. As you folks can see, if x and c together makes the recourse problem feasible, we don't need the y tilde if we want to minimize the L1 norm of y tilde. But if the x and c make the recourse problem infeasible, y tilde will be non-zero. So this is the idea behind. So by leveraging the almost true feasibility concept, we define the worst case expected value subproblem for feasibility. So this is formulation. And actually for this new worst case, for this new subproblem, we can tell if the computation result is equal to 0, we can conclude X will be feasible regardless the scenario in the sample space. But if this value is positive, that means there exists some scenarios cause X infeasible, causing the second stage infeasible. For this new subproblem, I want to highlight the oracles we developed previously actually can be applied here to solve this worst case expected value problem for feasibility. And as a result, we can, if it's non-zero, if the optimal value is positive, we can generate a lot of scenarios as well. And with those scenarios, we can build our feasibility cutting set. For the idea is very similar to optimality, but left-hand side is just changed to 0. So regardless X, and I'm sorry, so after adding this cutting set, we are forcing the mass problem to generate X such that this worst case expected value for those scenario generated by this feasibility subproblem will be less or equal to 0. So this provides some support to deal with infeasibility issue. Okay, we can get rid of infeasibility issue by incorporating this feasibility cutting set. Indeed, in our numerical study, we found the feasibility cutting set probably is not small. Sometimes could be very large. So let's move on. So here, let's summarize our whole framework to deal with the two-stage DRO. We solve the main mass problem to create a new lower bound and also to generate a new X star, the incumbent solution. And then we pass X star to the worst case expected value problem for feasibility. And if the value of this worst case expected value for feasibility is positive, we're going to generate a set of scenarios to implement our feasibility cutting set. If this X star can pass the feasibility check, we're going to solve the worst case expected value for optimality, which is the one we discussed in the previous section. And then when we generate scenarios for optimality and also upper bound. So the whole thing become an iterative procedure. We do it over and over until the lower bound upper bound can be matched. In that case, we can conclude we derive the optimal solution. So we're done with our basic framework. Let's see some exciting result. I'm sorry. Let's see some how to leverage this result, this framework to deal with a few extensions, to deal with a little bit more complex situations. One situation is how to address the Wasserstein ambiguity set. I believe many of you folks already have heard about the strength or the effectiveness of Wasserstein stat. The Wasserstein stat actually is defined by the Wasserstein distance, which is the optimal distance between two distributions. I guess I can skip this part a little bit. So by using this distance, we can define Wasserstein ball or Wasserstein stat. This is Wasserstein ball to define the constraints to define distributions such that the distance between the target distribution with respect to the reference one is less or equal to r. So r is to denote the radius. In the current literature, we treat the PN and we treat the reference distribution is made by our observation. So we assume Kasi, which is the data we have right now. It's a finite data set. So this data set provides the reference distribution. Okay. And for this one, again, we have integration, but this integration actually can be decomposed. So if we introduce the conditional probability pi for each observation, then the whole Wasserstein set can be decomposed largely. So we instead of determining a single distribution, we determine a distribution for each Kasi EI. They are work jointly together to meet the Wasserstein distance restriction. Okay, but this structure actually is very interesting because, as I mentioned, instead of consider a single distribution, we consider a set of distributions. So in our framework, it provides a great support to implement the parallel computation. So instead of consider a single pricing subproblem, as we highlight here, we're gonna deal with multiple pricing subproblem. Once we receive the shadow price from the pricing master problem, we can pass the pricing information to each of them, and they are independent. As you folks can see here, we can have a pricing subproblem for each observation, and they are independent to each other. So that allows us to implement the parallel computation. Okay. Indeed, we can see in our numerical study, we see the parallel computation can speed up 3 to 5 times faster compared with the serial computation. Okay. I don't cover the detail too much. If you folks want to know more, you can check this paper. It's posted in archive. In that paper, we demonstrate the effectiveness of the parallel computation. So this is one extension. Another extension we want to deal with is decision-dependent uncertainty. We have seen a research trend over the last few years. People instead of consider a static ambiguous set. Right now, the trend is this ambiguous set actually is a function of a first state decision. So instead of static one, right now it's function. It's a function of x. This one actually reflects some real situations. We heard the induced traffic, demand response, or maintenance. Those situations nicely demonstrate the decision-dependent uncertainty. Now, to deal with this new type of modeling scheme, we also can modify our framework a little bit to perform the computation. So let's assume gamma I right now is gamma ix, and psi the constraint inside moment constraint Right, psi right now is converted to psi x c. So as you folks can see, both are function of x. But for our framework, we don't need to worry about the impact of the subproblem, like a pricing mass problem and a pricing subproblem, because for those subproblems, x are fixed. So we don't need to worry about the changing x. The only change we need to care about is our main mass problem. So here I give you the structure of main mass problem. So traditionally this is gamma and psi, but right now it becomes gamma x and psi x. So as long as we can compute this main mass problem, we will be able to solve the decision-dependent uncertainty challenge. So the framework actually is pretty general to handle this. Let's move on. Another extension we did is, given the current popularity of AI, we're thinking, can we leverage AI to strengthen our performance? So one idea we're thinking is maybe we can use AI to help us to predict scenarios because, as we argued, our framework is a primal driven, primal perspective. So the key component in our process is identify the scenarios behind the worst case expected value. So we're thinking maybe we can leverage AI to help us to predict those scenarios. The particular AI tool we adopted is a generative adversarial network, which is a powerful neural network to learn the complex data patterns. So we were thinking train and use the train this GAN network and also using GAN network to predict the whole scenario set. However, the GAN actually is traditionally is a good and imaging video audio process. To leverage GAN in our framework, what we did is we customize a data encoding and decoding scheme. So for given set of scenarios, we try to convert scenario into a figure and use a figure to train our GAN network. And then finally, the GAN network will be able to predict another figure. And we're going to decode the figure into scenarios. So here we have a figure to demonstrate the whole process. For a given feature, basically you folks can interpret the feature as a given x. So given the first stage decision, we can generate our scenarios. The scenarios in our case actually we can binarize the scenarios. So they are like a 0, 1 vectors. And those scenarios are with their probabilities. And we can do a little bit more adjustment. So those scenarios can be treated equally. And then by using sampling, we can draw a lot of samples on our scenario set. As I mentioned, the scenarios are binary, so we can generate a lot of similar binary scenarios, binary labels, and binary labels we can convert into like a black and white vectors. By doing some sorting, the black white vectors can be converted into figures. So by using different seeds, we can create different figures. So we're gonna use those figures to train our GAN network. So this is the idea behind for encoding. For decoding, similarly, once we have this binary figure, a black and white figure, we can convert the figure into scenarios. And we found this one actually is also very useful. I don't cover too much details. If you folks interested, you can check this paper. It's also in archive right now. This figure is in archive. So well, I'm done with our extensions. Right now, let's see some exciting part regarding our numerical study. The first one I want to report to you folks is the comparison between these two oracles. As I highlighted at the beginning, the first one is mathematically clear, more rigorous, but computation-wise may not be so good. Actually, here it's come from our basic understanding. So I compare these two figures in a test situation. We set the time limit to 600 seconds. This part we deal with the continuous sample space. This part we deal with the discrete sample space. For the continuous sample space, actually the Oracle one have a hard time. Basically, Oracle one cannot produce the meaningful result within the 600 seconds. The gap sometimes they have a gap, sometimes they don't. Even for the gap, it's a huge. But for Oracle 2, the worst case by value can be solved instantaneously, negligible time. For the discrete sample space, Oracle 1 has a better performance. Sometimes it can produce optimal solution, but still the optimal solution may require a non-trivial amount of time. But same thing for Oracle 2, its behavior is very consistent. Uh, Basically 0 second, we can obtain the optimal solution. So in our primary numeric study, we are using Oracle 2 as our procedure subroutine to support our CCG framework. So for our general computation study is performed on a first location problem. We consider both uncapacitated and capacitated, and we consider continuous sample space, which is which is used to describe the random demand, and also we consider discrete one, which is used to consider the disruption on the facilities, and also we consider both moment and the Wasserstein ambiguous set. The time limit is 7,200 time. We care about the number of iterations and the gap if the algorithm cannot conclude within the time limit. So this is case for uncapacitated. Because we have a lot of numerical results here, I just provide a few of them. If you're folks interested, you can check the paper. For uncapacitated case, we consider this table is for the moment-based distribution, moment-based continuous one, so it's the demand. And indeed, we compare 4 different algorithms. Excuse me. In addition to CCG and CCDRO, the one we developed for this two-stage DRO, we also notice Benders is another popular algorithm in the literature. So we have we name it basic Benders, but we can also extend Benders with respect to our new subroutine for the worst case expected value. So this new extension is called it's called Benders with TRO. So we benchmark this 4 type of algorithm. We see that our new development CCDRO it's way much faster than the basic CCG. For small scale problem, it's 10 times faster, but for large scale, the difference is huge. It's kind of 100 times faster than the basic CCG we did a long time ago. And benders basically they are most of the time they are exceed the time limit. Although the benders with DRO can improve a lot, but still not able to solve the instances in a reasonable amount of time. So this is the case for the moment-based ambiguous set. Next, I can show you the performance for the Wasserstein based set. So for the Wasserstein-based ambiguous set, we see the difference is not so much anymore, but still it's pretty. The CCDR has a great advantage. For small scale, it's about 20 times faster. Large scale, for large scale, because the time limit is going to be exceeded very often, so we can roughly conclude it's a 10 times faster or 10 times to 20 times faster. So the difference is not huge, but still it's like a 1 order to 2 order magnitude faster. Excuse me. There's a few observations I want to share with you folks, quite interesting. We found ambiguous set on the discrete sample space actually could be harder to solve from time to time. This is kind of counterintuitive to what we have, what we thought at the beginning. And DRO is built on the Watson system, and being said actually could be easier because we noticed the number of iterations could be much smaller. At the beginning, we mentioned a classical result by Shapiro is there exist at most m plus one non-zero probability scenarios. But we found this theoretical result is confirmed in our CG-based Oracle tool. Here, I want to show you folks. Uh, like this case, the whole algorithm complete in within one iterations. The number of scenarios we generated is 51. But the sample space, the empirical observation we have is 50. So we have 51 constraints in our ambiguous set definition, but 51 constraints leading to 51 scenarios identified by our Oracle tool. So you can tell the theoretical result actually is confirmed by our numerical study. This is a quite interesting part. Another part is I want to mention is actually we can prove the CCDRO is able to dominate CCG in both lower bound and upper bound. That's reason behind why the DRO part, the DRO extension can be so much faster than the original basic CCG. I didn't show the feasibility, but you folks can check the paper, which is listed here. The feasibility part is non-trivial. The number of scenarios we generate for feasibility can be 10 times more than the number of scenarios we generate for the optimality. So the feasibility cannot be ignored. Here, I just want to show you the real life example, which is we did for the capacity planning uh, in a context of the beverage producer. We have a first stage and we have a second stage. In the first stage, we are trying to adjust our production capacity over 4 different seasons over multiple sites. And in the second stage, we're gonna produce a beverage to meet the demand. We have multiple beverage to meet the demand in the market. So the middle one will be the weather. So formulation is pretty complex, so I wouldn't go to detail. Okay. So this is a formulation. We have a first stage, a second stage. This is a recourse part, second stage. So for this particular application, we tried our GAN network integration, where the first figure, the figure above, shows the training process. So if you know a little bit of GAN network, it involves two parts. We supply the real figure, and we also supply a set of white noise. So the white noise is called a fake figure. So and before here we show the training process. So at the beginning in epoch 0, you folks can see there's no similarity. But after training over and over, the fake one actually looks like exactly to the real one. So that means the GAN network is able to learn the hidden pattern behind the first stage decision and the scenarios we're gonna predict. So the prediction of the scenario will be high quality. So we integrate after training, we integrate GAN network in our CCG framework, CCGDR framework. So the lower figure shows the performance improvement. And we notice that, let me explain. The blue bar is representing the basic CCG. The purple one is the CCDRO, and the yellow one is the AI enhanced CCDRO. It is interesting to notice that the AI integration actually can reduce the computation time for both the mass problem and also subproblem. It's quite interesting. We thought it should be faster, but it reduced the computation time for both the mass problem and subproblem. For details, you folks can check the paper. Okay, so here I'm gonna provide a few takeaways. The key takeaway is we want to say primal perspective open our horizon, and it provides a lot of useful interfaces and tools for us to make analysis and computation easier. And also, it's easier for us to appreciate the DRO concept because once we have scenarios, we know we can solve a simple linear program to get the allocation of the distribution on those scenarios, and to maximize the worst case to maximize the worst case distribution to maximize the worst case expected value. So this angle make the understanding easier. And another part is regarding the CCDRO algorithm. It is pretty general. It handles feasibility, and also we can extend it to handle the non-convex ambiguous set. We can handle decision-dependent uncertainty, and indeed in the paper we show it has a finite convergence guarantee. As a framework, as a platform, it opens a lot of opportunities for us to have more add-ons. One add-on is we can integrate with AI, and also we can implement it in a parallel computing environment, and both of them actually demonstrate the improvement of the computation performance. Overall, we noticed it could be like two orders, three orders magnitude faster than the current state of art. So it gives us a lot of support to deal with real life problems. I think this is the last page. Thank you much. I'm waiting for questions.